Hello everyone. Today we're diving into principal component analysis, or PCA, an advanced technique in factor analysis that's essential for working with high-dimensional data. In today's video, we'll cover 5 key topics that will help you master PCA. First, we'll explore the fundamental concepts and methodology behind PCA. Then, we'll look at how component variability works and why it matters. We'll also examine the relationships between loadings, eigenvalues, and eigenvectors. After that, we'll learn how to use Scree plots to select the optimal number of factors. Finally, we'll put everything into practice by implementing PCA using Python's scikit-learn library. Let's start by understanding what PCA really is. Factor analysis is a two-step process involving factor extraction and factor rotation. PCA is a specific technique that finds orthogonal components, which means each component is independent of the others. What makes PCA special is how it organizes these components. It maximizes variability in successive components, with the first component containing the largest variability and each subsequent component containing less. When we work with PCA, it's important to understand how component variability works. The maximum number of components we can have equals the number of features in our dataset. But the beauty of PCA is that we usually don't need all of them. The first component always captures the highest variability, which makes PCA perfect for simplifying our analysis while maintaining as much information as possible. Now let's talk about eigenvalues, which are crucial in PCA. An eigenvalue tells us how much variability is explained by each factor. Here's something interesting. The sum of all eigenvalues equals the total number of features in your dataset. We calculate eigenvalues by summing the squared loadings, and they help us determine the percentage of variance explained by each component. Understanding eigenvectors is another key aspect of PCA. Eigenvectors represent the direction of our factors and are made up of the coefficients of our input features. When we multiply an eigenvector by the square root of its corresponding eigenvalue, we get our factor loadings. This relationship helps us interpret what each factor means and how important each feature is. Let's discuss Scree plots, which are incredibly useful tools in PCA. A Scree plot shows eigenvalues plotted against factors, and it helps us decide how many components to keep in our analysis. The key is to look for the elbow, or point where the plot starts to level off. We typically select the factors before this leveling point, which helps us balance between keeping important information and simplifying our model. Here's a practical example of implementing PCA in Python using scikit-learn. This code shows how to initialize a PCA model, fit it to your data, and extract the loadings. The library provides several useful attributes like components, explained variance, and variance ratios that help us understand our results. To wrap up our discussion of principal component analysis, let's review the key points. PCA is a powerful technique for reducing dimensionality while preserving important information in your data. The components are organized to maximize explained variance, with eigenvalues and eigenvectors providing crucial insights into your data's structure. Scree plots help us make informed decisions about component selection, and tools like scikit-learn make implementation straightforward. PCA has wide-ranging applications in data preprocessing, feature extraction, dimensionality reduction, and data visualization. Thanks for watching. If you enjoyed this video, please like, share, and subscribe for more content on data science and technology. See you next time.